So let's next try to understand the relationship between rapidity and ordinary velocity. To this end, let me draw once again the unprimed frame with basis vectors E0 and E1, as well as the primed frame, F primed, with basis vectors E0 primed and E1 primed. Let's now consider an object that is co-moving with the frame F primed. So we have an object that relative to F is moving with a certain velocity, and it's the same velocity with which the frame F primed is moving. So the world line of our object is parallel to the basis vector E0 primed. You can also visualize it like this. We have our unprimed frame, and then we have our primed frame. Now the picture that I just drew, that's a picture in space-time. The picture that I'm drawing now on the right, that's an ordinary spatial coordinate system. So that's not a space-time diagram. So whereas here you have E1 and E0 representing time, in the drawing here on the right, these are spatial coordinates. And let's say that the frame F prime is moving relative to the frame F with velocity v, and so is the object. There's an object here that is also moving with velocity v. So seen in frame F primed, the object is at rest, but seen in the frame F, the velocity is moving with velocity v. Now let's go back to the space-time diagram on the left, and let us consider a specific event, say this event here. This event has, in the unprimed frame, coordinates x0 and x1. Now, since the object is moving with velocity v in the unprimed frame, it must be true that x1 is equal to velocity times t, and I can, rather than t, I can also use my new space-time coordinate x0. I can also write that as velocity over c, velocity of light, times x0. These are the coordinates seen in the black frame, the unprimed frame. What about the coordinates of this event in the blue frame, in the frame F primed? Well, relative to the primed frame, the object is at rest. So at any time, the object is at spatial coordinate x1 prime equal to 0. So this event has, let me try to indicate it like this, has coordinate x1 primed, which is equal to 0. How are x1 primed, so the primed coordinates and the unprimed coordinates, related to each other? They're related by a Lorentz transformation. In particular, we know that x1 primed that is minus hyperbolic sine of rapidity times x naught plus hyperbolic cosine of rapidity times x1. That's the transformation law according to the Lorentz transformation. So we apply this 2x2 matrix that we had seen on the previous page. Lambda is hyperbolic cosine, hyperbolic sine. This is the matrix that effects the transformation from unprimed to prime coordinates. So this means for the component x1 primed, it means the equation that I just wrote. But now we can use the fact that for the object x1 is given by velocity over c times x naught. Okay? So we can write that as, we can take x naught outside the bracket, we can write that as minus hyperbolic sine of rapidity plus velocity over velocity of light times hyperbolic cosine of rapidity times x naught. But at the same time we know from our simple sketch that x1 primed is equal to 0 because in the co-moving frame the object is at rest. So x1 primed is always 0. This is what we wrote up here. x1 prime of the event is 0, and that's precisely what we are using here. Now this implies an equation for rapidity. If this is supposed to be 0, and that must hold for arbitrary values of x naught, then the bracket in front of the x naught must vanish. So in other words, v over c times the hyperbolic cosine must equal the hyperbolic sine. We can divide by the hyperbolic cosine, and then we have v over c must equal the hyperbolic tangents of psi. So this implies that v over c is the hyperbolic tangents of psi, or in other words, the rapidity psi is the inverse hyperbolic tangents of v over c. This is the relationship between rapidity and ordinary velocity. Now for small arguments, the inverse hyperbolic tangents of x is approximately equal to x. Because it has, at x equals 0, this function has slope 1, and therefore for small arguments, it's approximately equal to the argument. So we have the result that this is approximately v over c for velocities much smaller than c. So up to this constant of proportionality, the 1 over c, rapidity for small velocities, rapidity is approximately equal to ordinary velocity. When we use this result for the rapidity, we can also express the hyperbolic cosine and the hyperbolic sine of psi in terms of ordinary velocity. For that purpose, you just have to know some relationship between the hyperbolic functions, between cosine, sine, and the tangents, but that's not so difficult. Then you find that the shape of the Lorentz transformation, or the entries of the Lorentz transformation, now read the hyperbolic cosine, that's 1 over the square root of 1 minus v over c squared minus the hyperbolic sign. This is minus v over c divided by the same square root, and here the same v over c divided by the square root, and finally 1 over the square root. So you see that it's a lot easier to express the Lorentz transformation in terms of rapidity. It's a much more compact notation. But here you have it in terms of ordinary velocities. And what you can take away from that is that for small velocities up to this factor c, rapidity equals ordinary velocity. But you see immediately that for large velocities, they start to differ. Now we have all the mathematics, and now to conclude, I would like to show you just a few famous relativistic effects and how you can understand them within this framework. The first of these is not really an effect, because it's just an illustration of an assumption that we put into the theory. So it's not a new insight, because the fact that the velocity of light is the same in all reference frames, that was one of the key assumptions that we made, so it's nothing new. But I would like to show you how you can see that immediately in these space-time diagrams. Here's the unprimed frame. This is the primed frame. Now a light ray in the unprimed frame has a world line. It's a straight line that, and the light is traveling at the velocity of light, of course. And it's just a diagonal. This is a world line of a light ray. And you see in the unprimed frame, after 1 unit of x naught, the light ray travels 1 unit of x in the spatial direction. Now in the primed frame, it's exactly the same. In the primed frame, after the light ray has traveled for 1 unit of x naught, so this dashed line here indicates simultaneous events in f primed. This dashed line is parallel to the E1 primed axis and denotes events of constant time in the primed frame. So, and if I go sort of 1 unit of time in the primed frame, that means I go along this E0 prime basis vector. That's after 1 unit of time. And then if I want, then I'm at this event here. This event is after 1 unit of time, or 1 unit of x naught in the primed frame. And then I ask, where is it in the in terms of the spatial coordinate? Now, to measure the spatial coordinate of this event, I have to go parallel to the basis vector E0 prime. So this is this dashed line here. These are all events with identical spatial component x1 primed. So I go along this dashed line and I measure the x1 primed component of this event, and I see again it's 1 unit. So in the primed frame, I see the light ray travels 1 unit in the spatial dimension after 1 unit of time, or x naught, and the same in the unprimed frame in F. I also measure that the light ray travels 1 unit of spatial distance after 1 unit of time. So in both frames we measure the same velocity of the light ray. In both frames we measure the light ray travels 1 unit of spatial distance after 1 unit of x naught, which up to the factor c measures time. Okay, so this is how you see the universality of c directly in these diagrams. Now let's come to true relativistic effects. One famous effect is that the notion of simultaneity of two events is no longer absolute, but different observers have different notions of simultaneity. So two events which for one observer are simultaneous are not necessarily simultaneous for another observer. Non-relativistically, simultaneity is the same for all observers because time is absolute, time is the same for all observers. And obviously, this implies that also simultaneity is absolute and the same for all observers. But relativistically, these are again our two frames in space-time. And let's look at two events. Say here event number 1 and event number 2. In the unprimed frame, these two events are simultaneous. We measure the same time coordinate. So x naught of the first event, or maybe I should call them A and B rather than 1 and 2. Let me call them A and B. So x naught of A equals x naught of B, and this means x naught up to the factor c, this is time, so t A is equal to tb. What is the time that the primed observer measures? Well, to measure time, the time coordinate of event A, I have to go parallel to the E1 primed axis, and then I will measure x naught primed of A. And to measure the time coordinate of event B, I also have to go parallel to the axis. And I measure xb naught primed. And you immediately see that x naught prime of A is different from x naught prime of B, and hence the time measured in the primed frame for event A is different from the time measured for event B. So these two events are simultaneous in F, but not in F primed. So it's a direct consequence of the fact that this basis vector E1 prime is rotated, is tilted with respect to E1. This means when we measure the time coordinate of events, we have to go parallel to this tilted axis, and this implies that what's simultaneous in one frame is not simultaneous in the other frame. Another very famous effect in special relativity is time dilation. Certainly you've heard of the famous twin paradox. So a twin brother who travels in a very fast rocket and then comes back to Earth comes back younger than the brother who stayed on Earth. So clocks that move seem to move more slowly. And I would like to show you qualitatively how you can understand this effect in these space-time diagrams. So once again, we have F, and we have the frame that is moving relative to F. This is F primed. And now we take a clock that is moving at the same speed relative to F as the reference frame F prime, as the observer F prime. So the world line of the clock, of the moving clock, is parallel to the time axis of F primed. So in the reference frame F primed, the clock is at rest, and relative to F, the clock is moving. So let's say the clock ticks. It's a mechanical clock. It makes tick, 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 tick. And let me denote by these red dots. Each red dot is a tick of the clock. So it makes tick, 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 and so on. Now this here, what I denoted with this brace, that is one time unit in F primed. So we go from the origin of this space-time reference frame, we go to the tip of the basis vector E naught primed, and this corresponds to one time unit in the primed frame. And in this time unit, the clock ticks n times. So n ticks in one time unit in F primed. The observer F also sees the clock ticking, and after one time unit, that would be here, this dashed line, that corresponds to time equal to one time unit. Now look at the ticks along the world line of the clock. Seen by observer F after his or her first time unit, there are fewer ticks than in one time unit of F primed. Yeah? So the way I just drew it, there's one tick less seen by the observer F. Because this one time unit is over, where I drew this horizontal dashed black line. These are all the events after one time unit in F. And now you just count the ticks on the world line of the clock up to this dashed line. And there's one tick less. So observer F sees this moving clock, and observer F sees that in his or her time unit, the clock shows fewer ticks, and this means that the clock goes more slowly. So here, observer F sees less than n ticks in one time unit in F. And therefore, seen in reference frame F, the clock appears to tick more slowly. So the green line, that's the world line of the clock. Each red dot is a tick. Now, observer F primed counts the number of ticks during one time unit. One time unit means going along just from the beginning to the end of the basis vector of time, the basis vector E naught primed. This here is the basis vector E naught primed, whereas that is the basis vector E naught. Yeah, so the primed observer f prime goes along the basis vector E naught primed. That corresponds to one time unit, and within this one time unit counts n ticks of the clock. So the observer sees that the clock ticks at a rate of n ticks per time unit. The observer f also counts the number of ticks, observes the clock, counts the number of ticks within his or her one time unit. So going also along this basis vector E naught, unprimed, which corresponds to one time unit in the unprimed frame. And the observer f counts fewer than n ticks. So the observer f sees that the clock ticks at a rate of less than n ticks per time unit. And therefore, for observer f, the clock appears to tick more slowly. This is the qualitative explanation. The quantitative result is that the ticking rate of the clock differs by a factor hyperbolic cosine of rapidity, and we had seen that this is nothing but 1 over square root 1 minus v over c squared. So this factor is, which is always larger or equal to 1. So this is the factor by which the ticking rates of the clock differ in the two frames. Yeah? And the reason for that is that in the direction of E naught, or sort of the E naught component of that basis vector E naught primed is not 1, but it's the hyperbolic cosine of psi. Yet another famous result of relativity is length contraction, saying that if an object passes at high speed, it appears to be shorter than if you look at it when it's at rest. Once again, let's try a simple explanation in these space-time diagrams. This time, rather than a clock, I would like to consider a rod, a measuring rod. And now this time I would like to consider this rod to be at rest in the frame F. So the world line of this rod is going up vertically. Yeah? And I would like to distinguish the left end of the rod and the right end. The left end has this world line going up vertically. It's at rest in frame F. And this is the world line of the right end. The rod has length of 1 unit in frame F. So it's at rest in F, and it has length 1 in F. How do you measure the length of an object, in this case of this rod? you measure simultaneously the position of the left end and the right end, and then you look at the distance between the two, difference between the two. That's also what observer f prime will do. So observer f prime will look at the left end of the rod and the right end of the rod at a certain time, so the same time simultaneously in f prime, and we'll take the difference of the space coordinates, and that this difference equals the length measured in f prime. We already know that simultaneity is not the same in f and f prime, whereas in f, the two green dots that I indicated here in this drawing, this green dot here on the left and on the right, these are simultaneous events in f. They have two different spatial values for the spatial coordinate, and the difference between the two values, that's the distance measured in f. What will f prime do? F prime will also, on the world line of the left end and on the world line of the right end, will take two events which are simultaneous. So, for example, this one here and that one. These two red dots correspond to our events. They are simultaneous in f prime, and they relate to the left end and the right end of the rod. The length seen by observer f prime is this distance that I indicated with the brace. Yeah? This is the length of rod seen in f prime. It's the difference between the spatial coordinates of the left end and the right end of the rod, measured simultaneously in f prime. But you see, this length, this distance is shorter than the basis vector, the blue basis vector. It's shorter than this vector E1 prime. And therefore, it's less than 1 unit in f prime. So whereas in the observer f sees that this rod has length equal to 1 unit, the observer f prime sees that the rod has length less than 1 unit. So in the frame where the rod is at rest, namely in f, it's 1 unit. In the frame f prime, which moves relative to the rod appears to be shorter. Then let me come to the last relativistic effect that I would like to discuss, and that's the relativistic addition of velocities. You immediately see that there is a problem with the ordinary way of adding velocities. For example, when you stand at the platform of a train station, a train passes by with a certain velocity, say 50 kilometers an hour, and then inside the train a passenger is walking in the same direction in which the train is moving, say at a velocity of 10 kilometers an hour, then you on the platform see this person moving at a velocity of 60 kilometers an hour. It's just the sum of 50 and 10 kilometers an hour. But when you go to very high velocities, then you see that there's going to be a problem. Say you now imagine that you have a train moving at 3/4 the speed of light. And then inside the train you have a light signal moving at the speed of light relative to the train. And then if you use the non-relativistic law for adding velocities, then on the platform you would see the light signal traveling with a velocity of 1 plus 3/4. So more than the speed of light. But that would contradict the basic principle of special relativity, that nothing can travel faster than the speed of light. So how does the theory circumvent this difficulty? Without further proof, I would like to state that Lorentz transformations form, mathematically, they form a group. We had looked at that, and you had also worked on that on one of the first problem sets for the Galileo group. We had proven that the Galileo transformations form a group. The same is true for Lorentz transformations. So when you go from a frame F to a frame F primed that moves relative to F with a velocity v1 and a corresponding rapidity psi1, and then you go from F prime to another frame F double prime, which relative to F prime moves with rapidity psi2, then this is equivalent, the end result is equivalent to going directly from F to F double primed, where F double primed moves relative to F with rapidity psi1 plus psi2. So rapidity is additive. You can see that mathematically by considering Lorentz transformations in the form that we derived. So the first Lorentz transformation going from F to F prime, this has this form hyperbolic cosine of psi1 minus sine psi1 minus sine hyperbolic psi1 and cos psi1. The second transformation has the same form, only with psi2. Yeah, so you apply that to, it's the same form. You can do the matrix multiplication and use the properties of the hyperbolic functions. They are similar to the ones of the ordinary trigonometric functions. And you can, using these properties of the hyperbolic functions, you can see that this is equal to the hyperbolic cosine of psi1 plus psi2 minus the hyperbolic sine of psi1 plus psi2 minus the hyperbolic sine of psi1 plus psi2. And from this you see that's sort of the mathematical expression, the mathematical proof of the statement that I gave above, that going from one frame to the next that moves with rapidity psi1, and then yet to another frame that moves with rapidity psi2 is equivalent to going directly from the first frame to the last frame, where the rapidity is psi1 plus psi2. So rapidity is additive, but velocity is not. It is true, of course, that for velocities v1 and v2 much smaller than c, we know that the rapidity is approximately v over c. And therefore, if rapidity is additive, then velocity is additive. That's in the limit of slow velocities. Yeah? But when you come close to the velocity of light, then you really have to work with rapidities, and they are additive. And let me just give you an extreme case, namely that v1 and v2 are both equal to the velocity of light. This implies the rapidity. What is the rapidity if the velocity is equal to the velocity of light? Rapidity was the inverse hyperbolic tangents of v over c. v over c is 1, and the inverse hyperbolic tangents of 1 is infinite. Maybe I should write it also here as a limit. Yeah, so v1 and v2 approach the velocity of light. This implies that the rapidities approach infinity. This implies that psi1 plus psi2 obviously also approaches infinity. And this implies that v, that's the velocity of f double prime relative to f, again approaches c. It doesn't go beyond c. There is also an explicit formula for the addition of velocities, but the key message here is, relativistically, it's not velocities which are additive, but it's rapidities which are additive. And this rule makes sure that as you approach the velocity, even as you approach the velocity of light, so one observer is moving relative to the other almost with the velocity of light, and relative to that observer there's yet another object almost with the velocity of light. Still, in the first frame, this object appears to move at a velocity which never exceeds the velocity of light. And that's thanks to the relationship between rapidity and ordinary velocity.